Euclidean Geometry part 15 of 25. Okay, we are going to see the theorem that says tangent to a circle from a common point. Okay, so figure 1, you have a circle with a center O, and you have a point P. From this point you have a tangent touching this circle at the point B. So let's call this tangent AC. Let's say we have another line which is a tangent from the same point P. Okay, so this line is a tangent to the same circle. Okay, so the tangent from the point B is touching this circle at the point E. Let's call this tangent DF. So line AC is a tangent to the circle at point B, and line DF is a tangent to the circle at the point E, and you have P, which is a common point for these lines, for this tangent. Okay, the tangent from a common point P. This theorem says BP, okay, BP is equal to EP. Okay, and the reason for this, you are going to say tangent from a common point. So you can write your reason like this: tangent, okay, tangent, we have 2, okay, tangent from a common point. In this example, the common point is P. Okay, so whenever you have this situation, you have to know that this distance, okay, BP is equal to EP. Now, in figure 2, you have a circle with the center O. You have a tangent to this circle. Let's call it RT. Okay, RT. This tangent is touching this circle at the point S. So if you draw a radius or a diameter from the point of contact, the point of contact is S. Okay, if you draw a diameter or a radius from the point of contact, this is what you have to know. The diameter or the radius is going to form an angle of 90 degrees with the tangent at the point of contact. So let's call this diameter SM or MS. So this angle which is formed between the tangent and the diameter or the radius is 90 degrees. In a diameter, you have 2 radii. Okay, you can also see that in figure 1. From the point of contact, you can draw a diameter or a radius from the point of contact. So the angle formed between the tangent and the diameter or the radius is 90 degrees. You can draw another diameter or another radius from this point of contact. So again, this angle is 90 degrees. So the radius or diameter is always perpendicular to the tangent at the point of contact. Okay, at the point of contact. Okay, 90 degrees angles. So in figure 1 you can come up with this. OB, okay, OB is perpendicular to AC. Okay, the reason is you have tangent radius theorem. Okay, this is the reason why OB is perpendicular to AC. The reason is you have tangent radius theorem. You can also say angle OBC. Okay, angle OBC. This angle OBC is equal to 90 degrees. The reason is you have tangent radius theorem. Okay, tan-rad theorem. You can also say OE is perpendicular to DF. Okay, OE is perpendicular to DF. OE is perpendicular to DF. Okay, in figure 1. So the reason is tan-rad theorem. Okay, tangent radius theorem. Okay, tangent radius theorem. You can also say the angle OEF. This angle is equal to 90 degrees. The reason is tan-rad theorem. Or you can say angle OED. This angle is also equal to 90 degrees. The reason is tangent radius theorem. Okay, this angle is also 90 degrees. Angle OED, or this angle OBA. Okay, now in figure 2. Okay, from figure 2 you can say MS is perpendicular to RT, or you can say OS is perpendicular to RT. Okay, MS is perpendicular to RT. So the reason is tangent radius theorem. Okay, tangent radius theorem. This is why you have MS or OS perpendicular to RT. Remember, in a diameter you have 2 radii. Okay, this is a radius, this is another radius. Okay, so this is the reason why you have MS perpendicular to RT. You can also write this angle. Okay, angle MST. Okay, MST. Okay, angle MST. MST or OST is equal to 90 degrees. The reason is tangent radius theorem. Okay, we are done.